Now that we know how to handle limits, we're going to use limits to help us find derivatives. So we're going to jump into Chapter 2 and deal with Section 2.1, which talks about the derivative and the tangent line problem. Thinking back to algebra, we know that the slope of a line is represented by m, or the change in y over the change in x. Here is a visual representation of slope. Change in y, change in x. A secant line is a line that touches a curve in 2 points. A tangent line is a line that touches a curve in 1 point. The tangent line problem, which we said was one of the main reasons why we need calculus, is how do you find the slope of a tangent line to a curve at any given point? Here's a visual representation of a function f of x and a line tangent to that function. The question is, what is the slope of the tangent line at that exact point? In order to find the slope of the tangent line at a specific point, we're going to use the difference quotient. The difference quotient gives us the slope of the secant line. However, if we want to know the slope of the tangent line at any given point, we are going to find the limit as delta x, or as we talk about it, h approaches 0 of our difference quotient, assuming that the limit does exist. So in order to find m, our slope, we are finding f prime of x, which is one way that we can represent derivatives, by finding the limit as delta x approaches 0 of our difference quotient. Before we start calculating derivatives, we need to talk about a few notes about derivatives. Differentiation is the actual process of computing a derivative. F prime of x, as seen on the last slide, is the slope of y, which is equal to f of x, at x. The line through the point, the ordered pair x, f of x, with slope f prime of x, is the tangent line to the curve at point P. There are several different ways that you can indicate derivatives. The first three are our primary ways that we are going to represent derivatives in our class. The first is f prime of x. Second, dy over dx, which means the derivative of y with respect to x. And the third is y prime. We're not going to be too concerned about the fourth and fifth way to show derivatives. If we're asked to find the slope of the tangent line to the graph of our function f of x equals 3x minus 1 at the ordered pair 2, 5, that means we need to find the limit as h approaches 0 of our difference quotient. So let's start by writing our difference quotient. Limit as h approaches 0 of f of x plus h minus f of x all over h. Now in order to calculate the difference quotient, we need to take x plus h and plug it into our original function for x. So we now have the limit as h approaches 0 of 3 times the quantity x plus h minus 1. That's the plug of the x plus h into our original. Then I'm subtracting the original f of x function, so minus the quantity 3x minus 1 all over h. These parentheses here are important because we're subtracting that whole function, therefore I need to distribute this subtraction into both pieces. I must also distribute the 3, so let's continue cleaning this up. You'll remember from earlier that when we apply our difference quotient, it ends up cleaning up very nicely. So when distributing, we end up the limit as h approaches 0 of 3x plus 3h minus 1 minus 3x plus 1 over h. Now we need to start simplifying. We have a positive and a negative 3x. Those are going to cancel. Positive and negative 1, those are going to cancel. So we're calculating the limit as h approaches 0 of 3h over h. We can now cancel, and we know that if we're finding the limit of a constant, the answer is going to be that constant. So the slope of the tangent line to the graph of f of x equals 3x minus 1 at the point 2, 5 is going to be 3. You should also note that if we were to take our x value of 2 and plug it in for our x at any point, once we've started applying the difference quotient, we will also get 3 for our slope. That is because the graph of a linear function has the same slope at any point. Our 3x minus 1 is a linear function. Therefore, the graph of that function has the same slope everywhere. However, when we're dealing with nonlinear function, then we need to be careful as to what our x value is. Right here. So let's take a look at another example and you'll see what I mean. Our next example asks us to use the definition of derivative to find f prime of x if our function f of x is equal to x squared plus 3. You should notice that we have a quadratic function, so we're going to have to do a little bit more work if we are to find the slope at a specific point. So, in order to use the definition of derivative, that's asking us to find the limit as h approaches 0 of our difference quotient. So let's start once again by writing our difference quotient, f of x plus h minus f of x over h. We're going to start by taking the x plus h and plugging it in for our x in our original function. So we need to find the limit as h approaches 0 of x plus h quantity squared plus 3. That's the plug of the x plus h into the original. And then I'm subtracting the whole original function. So minus the quantity x squared plus 3 all over h. So we need to continue by foiling the x plus h quantity squared and distributing the subtraction into the x squared plus 3. When we FOIL, we will get x squared plus 2xh plus h squared plus 3 minus x squared minus 3 over h. We can cancel out our x squareds. We can cancel out our 3's. So we now have the limit as h approaches 0 of 2xh plus h squared over h. Now we still have a little bit of a problem because we can't use direct substitution 0 in for h, but we are able to factor out an h in the numerator. So the limit as h approaches 0 of h times the quantity 2x plus h over h. I can now cancel, and then to find f prime of x, find the derivative using our definition of derivative, also known as the difference quotient, we are finding the limit as h approaches 0 of 2x plus h. I no longer have a problem with direct substitution, so I'm going to take this 0 and plug it in for h. Be careful, it's the limit as h approaches 0, not x. So when we do that, we end up with 2x plus 0, which is simply 2x. This is our f prime of x. So I'm going to use this in order to find our slope at specific points below. We found our derivative above, which was f prime of x is equal to 2x. So now we are going to use f prime of x from above to find the slope of the tangent line at the specific points. So here's my x value for this ordered pair 0, 3. What we're going to do to find the slope, our m is going to be equal to f prime of x. We know that f prime is equal to 2x, so if I plug in 0 for my x value, I will find that my slope at this specific point is equal to 0. I'm going to do the same thing for b. I want to find the slope when x is negative 2. So I'm going to take negative 2 and plug it into my f prime of x. So it's going to be equal to 2 times negative 2, which is equal to negative 4, is our slope at that particular point, negative 2, 7. We're now going to use the slope and our given points to actually find the equations of the tangent lines at these specific points, using perhaps our point-slope form, since we have a point and we have a slope for each. In case you forgot, our formula for point-slope form is y minus y1 equals m times x minus x1. Our next part of the problem asks us to write the actual equations of the tangent lines at these specific points. Above, we found that the slope of the tangent line at the point 0, 3 is equal to 0, and the slope of the tangent line at the point negative 2, 7 is equal to negative 4. Since we now have an x, y, and m for each problem, I can plug into my point-slope form to have an equation of the tangent line. So for a, we have y minus 3 is equal to 0 times x minus 0. Well, 0 times anything is just going to be 0, so we can either write y minus 3 is equal to 0, or simply y equals 3. That would be a horizontal line. For b, plug in our x, y, and m. We have y minus 7 equals negative 4 times x minus negative 2, which is the same thing as x plus 2. Feel free to leave it in point-slope form, or if you'd like to rearrange, distribute, and put it in slope-intercept form, it'll be y equals negative 4x minus 1. Either answer would be acceptable. Through our process for the last couple problems, you should have found that in order to find the slope of a tangent line at a specific point, we need to first find our derivative, so far using the difference quotient, finding the limit as h approaches 0 of our difference quotient, and plugging in an x value. That will give us the slope at that specific point. Then, if we want to find the actual equation of the tangent line at a specific point, we first need to find the slope using the process above, and then plug in the point and the slope into our point-slope form. You can also plug it into your y equals mx plus b, your slope-intercept form. Our next example asks us to find dy dx with the derivative of y with respect to x if our function f of x is equal to 1 over x. Currently, our only way to find derivatives is to use our difference quotient and find the limit as h approaches 0. So, dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So I need to take my x plus h, plug it into my f of x function. So my dy dx is equal to the limit as h approaches 0 of 1 over x plus h minus our f of x function, so minus 1 over x, all over h. Now, if both of those fractions in the numerator are being divided by h, what we can do is we can take the h and put it into both of the denominators. So let's rewrite that as the limit as h approaches 0 of 1 over h times the quantity x plus h minus 1 over xh. In order to do this subtraction, because I still can't use direct substitution yet, I need to find an LCD. My LCD is going to be xh times x plus h. We need to include the highest power of each factor that we have in our denominator. So LCD is equal to xh times x plus h. So if I rewrite both of these fractions with our new denominator, I'm now finding the limit as h approaches 0 of what's in my new denominator that wasn't in my original for the first fraction. That's going to be an x. So we need to multiply that into my numerator. So I have x over xh times x plus h minus what's in my new denominator that wasn't in my original for the second function, second part of my function, and that was the quantity x plus h. So that gets multiplied in the numerator. So put that in parentheses for the subtraction that's going to be happening. So I can now do the subtraction and put the two fractions together, since I have a common denominator. So I'm now finding the limit as h approaches 0 of x minus h. Well, the two x's are going to cancel, so we're left with the limit as h approaches 0 of negative h over xh times x plus h. Oops. Since I have factors now, I can cancel an h in the numerator and an h in the denominator. So we'll move over here, finding the limit as h approaches 0 of negative 1 over x times x plus h. Now if I use direct substitution and plug in 0 for h, I don't have a problem. When I do that, I'm left with negative 1 over x squared. That is equal to dy over dx, also known as the derivative of y with respect to x. This is general. If I wanted to find the slope of the tangent line at a specific point, I could take any point, take the x value, and plug it in to my dy over dx and find the slope at any given point. That's what we're going to do in our next example. Alright everybody, buckle up for this one. We're going to need to find the derivative of f of x equals x cubed plus 2x. That will give us our general derivative that will allow us to find a slope out of the tangent line at a specific ordered pair. Well, after we find that general derivative, we then need to find an equation of the tangent line to the graph of f of x at this specific point. So once we find our general derivative, we can plug in 1 for our x to find the slope at that specific ordered pair, and then use point slope form in order to find the actual equation of the tangent line at that point. So let's start by finding the general derivative by using our difference quotient. So dy over dx, or y prime, f prime of x, whatever you'd like to write, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So we need to start by taking our x plus h, plugging it into both spots where we see an x in our original function. So we need to find the limit as h approaches 0 of quantity x plus h cubed plus 2 times x plus h minus our original function f of x, so minus the quantity x cubed plus 2x. And that's all over h. So now we need to do some distributing. We have to multiply some things out in order to clean up, hopefully, factor and cancel out that h in the denominator that has a problem. So the limit as h approaches 0. If you cube x plus h, you will end up with x cubed plus 3x squared h plus 3xh squared plus h cubed. We need to then distribute the 2, so plus 2x plus 2h, and also distribute our subtraction, so minus x cubed minus 2x all over h. That was just a lot of algebra. So let's see what we can cancel out. We have a positive x cubed, negative x cubed, positive 2x, negative 2x. Doesn't appear as though there's anything else we can cancel, but it is good because all of the terms we have left in our numerator do include an h, which means I'm going to be able to factor an h out of the numerator and cancel it with our denominator. So I'm out of room. So to erase and start fresh. So here we go. If I pull out an h in my numerator, we have the limit as h approaches 0 of h times a quantity 3x squared plus 3xh plus h squared plus 2 all over h. Our h's now legally cancel, and we can calculate our limit as h approaches 0 of 3x squared plus 3xh plus h squared plus 2. When I do direct substitution, I take 0, plug it in for h here and here. Those terms are going to go away. So our limit as h approaches 0, also known as dy over dx, f prime of x, or y prime, all ways that we can indicate derivative, is going to be equal to 3x squared plus 2. As I said earlier, this is what we can essentially call our general form, which will yield us the slope at any point of our tangent line. Okay, so I want to know the equation of the tangent line of our function at the ordered pair 1, 3. So that means I want to know the slope when x is 1. So let's take 1 and plug it in for x into our general form. When we do that, my m is equal to 3 times 1 squared plus 2. So my m is going to be equal to 3 plus 2, which is equal to 5. There is my slope. Here is my ordered pair. So if I go to my point slope form, y minus y1 equals m times x minus x1. We now have an equation, y minus 3 is equal to 5 times the quantity x minus 1. If you prefer slope-intercept form, you can rearrange it and make it y equals 5x minus 2. Either way would be acceptable on a quiz or a test. So here's the equation to the tangent line of our function at the ordered pair 1, 3. We started by taking the derivative of our original function by finding the limit as h approaches 0 of our difference quotient, gave us our general form, which then was able to give us our specific slope of the tangent line at a given point when plugging in our specific x value. And then we were able to use point slope in order to find our actual equation for the tangent line. For our last problem of today's lesson, we need to find f prime of x for f of x is equal to the square root of x. Once we find the general derivative, we then need to find the slope of the graph of f at the points below, points 1, 1 and 0, 0. So in order to find our general derivative, we need to find the limit as h approaches 0 of our difference quotient. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Just like always, we're going to start by taking x plus h, plugging it into our original function, and then f of x. So we have the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. We can't use direct substitution, put 0 in for h because we'll have a 0 in our denominator. So we need to rationalize. To rationalize, we need to multiply by the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. This is technically a form of 1. When I do that, I would need to FOIL in my numerator. When I multiply my first terms, square root times a square root, well, it's going to undo those radicals, so I'm going to end up with the limit as h approaches 0 of x plus h. When I multiply my outers and my inners, they're going to cancel each other out, and then square root of x times square root of x is going to give us x. Positive times a negative is going to be minus x in the numerator, and we can leave our denominator in factored form. There we go. Now you'll see we can cancel x's in the numerator. We're just left with an h in the numerator, and there's a factor of h in the denominator that can cancel. So now we have the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. When I use direct substitution and I plug in 0 for h, I have the square root of x plus the square root of x in my denominator, so that is going to equal 1 over 2 square root of x, which is my general form of my derivative, f prime of x. Question also asked us to find the slope of the graph at these specific points. So 1, 1 and 0, 0. So for A, draw a line here. For A, we're simply going to plug in our x value of 1. So f prime of 1 is equal to 1 over 2 times the square root of 1. Well, the square root of 1 is 1, so the slope when x is 1 is 1/2. That's our m, that's our slope. However, let's take a look at the order pair 0, 0. So for B, f prime of 0 is equal to 1 over 2 times the square root of 0. Well, the square root of 0 is 0. 2 times 0 is 0. So we get 1 over 0, which we know is undefined. So even though we eliminated our problem when we were finding the limit as h approaches 0 of our difference quotient, when we continued farther and tried to find the slope of the tangent line at a specific point, that being the origin, we came across a problem. These problems will be addressed in tomorrow's lesson.